In this segment, I want to talk just a little bit about atmospheric pressure. So, previously, I've said that within human-sized containers, a room or a jar or a box, the pressure of a gas really doesn't vary very much from the top to the bottom, not in a measurable kind of a way. However, if you're talking about very, very large containers or the atmosphere itself, then the pressure certainly varies with depth within a very large container like the atmosphere. And, we talk about the atmosphere, and there's really no line where the atmosphere ends and space begins. Really, we just have a large density at sea level. And as you get higher and higher in the atmosphere, the density gets lower and lower and lower. And at some point you say, well, you know what, there's hardly anything out there, we're going to call it space. But, even in interplanetary space, so, out somewhere between here and Jupiter, say, you're going to find a few hundred particles in a meter cubed, right? Maybe that sounds like a lot to you. But consider that in this room, in a meter cubed of air, you're talking about, 10 to the 24th or something like that particles, right? So 24 zeros of particles in a meter cubed here in this room. In between here and Jupiter, you're looking at about 100. So, almost nothing. It's kind of something, but almost nothing. If you look out there, in interstellar space, so, in between, say, our solar system and the nearest star, Alpha Proxima, you're looking at maybe 1 or 2 particles per meter cubed. So there's an occasional particle out there, but almost nothing. Again, it's not a hard dividing line. But the deeper in the atmosphere you go. And so we've defined this, we call it 1 atmosphere of pressure is 101,300 pascals. And that's sort of a standard average for a sea level pressure. Of course, it depends on the weather, but it also depends on your elevation. And so if you're down here at the bottom at sea level in, say, Seattle or San Francisco, I don't know, then all of the atmosphere is stacked on top of you. And there's higher density of air and also a higher pressure of air. As you go up, it gets lower. We here in Colorado, right here in Greeley, we're about 5,000 feet of elevation. And so we have something like 80% of the pressure that is at sea level. And so there's about 80% of the air density here in Greeley as there is at sea level. So it's actually fairly significant. If you were to go up to the top of Long's Peak, then you'd find that there was actually, about 60% of the air, right? So there's only 60% of the density and 60% of the pressure at the top of Long's Peak as there is at sea level. So that's a pretty big difference. And when you think about that, this the fact that, when your relatives come to visit you from sea level and you go up to Rocky Mountain National Park or something and they don't feel so good, you can really see why. There really is significantly less air. So top of Long's Peak, about 14,000 feet, only 60%. By the time you get to the top of Everest, which is about 29,000 feet above sea level, there is only about 1/3 of the atmospheric pressure as there is at sea level, which is why very few people have ever climbed Everest without using supplemental oxygen. Okay. Let's talk about how you measure air pressure really quick. I have here a container of water, and I've just added a few drops of green food coloring to hopefully make it so you can see it a little bit better. And here I have a glass, a very thin glass, I suppose. It's a vase, or I guess you could drink something very fancy out of it. Okay, so I've got a glass, and I've got my water here. And I'm just going to put my glass in here. And, those of you that have been stuck with the chore of doing dishes a handful of times in your life have probably made this discovery at some point in your life. It's really quite interesting. If I fill this glass up with water here, and then I invert it as I bring it up, what happens? Does the water flow out of it? No, it does not, right? And you can see here that this glass is full of water. You can see that slight green tint to it. It is currently full of water. Well, why? Why doesn't it run out? Well, there's no air at the top here, right? Because I put it in, I completely filled the glass, and then I brought it up, inverted. So there's no air up here at the top, no little pocket of air. And so what is the air pressure at the top of here? It's kind of weird to think about, but there's no air. There's kind of no air pressure at the top there. There's no air, right? So that's kind of weird to think about. But why does it go up in there? Well, pressure can only push, right? We think of suction cups as sucking. No. Suction cups are pushed on from the outside. There's a greater pressure on the outside of the suction cup, smaller pressure on the inside. A suction cup is pressed to this thing that it's stuck to. It's not sucked to the thing that it's stuck to, right? So pressure only pushes. Well, we've got atmospheric pressure pushing down on the surface of the fluid here in my Tupperware, and that pushes the water up into this cup. There's no air at the top of this to push down on the surface here, and so what happens? Well, the air is forced up into this cup. Now, if I was to draw this up, well, guess what? The water just comes with it. You can see that I've lifted it up higher, and guess what? It's still full of water, completely full of water. And I'm raising it up just a little bit more. Now I'm just about to break the surface of the fluid within the Tupperware. What's going to happen? Well, again, anyone that's spent much time doing dishes knows exactly what's going to happen. Once I let a little air in there, the pressure will equalize and the water will run out. And indeed it does. Okay, so, what's the height of this cup? I don't know. We're looking at 8 inches or something like that, right? What if I had a really, really long cup? Like, would this just keep working? Like, what if I had, a 10-foot long cup, let's say? Could I pull that 10-foot long cup up out of the water and still have it remain full of water? The answer is yes. How about a 20-foot long cup? Well, I can't demonstrate that because that's just not something I have in my cupboards upstairs. But if I had a 20-foot long cup, you know what? That works too. What about a 30-foot long cup? A 40-foot long cup? You know what? At some point, it doesn't work anymore. And that's just over 30 feet. Right? So if I had a 35-foot long cup, or tall cup, I guess, and I pulled it out, guess what? When I got it 30 feet, something like 30-something feet above the surface of this water, guess what? The atmosphere would no longer be able to push hard enough to keep all of that water in the cup, and you would start to see a little bit of separation up here. Separation between the bottom, well, now it's the top, but the inside top of this cup and the top surface of the water. You'd start to see a separation. Now, it wouldn't be air that's filled up in there because there's no air in my cup. It would actually be a vacuum. It would be empty space. Why? Because there's only so much atmospheric pressure. This atmospheric pressure can only support a column of water that's so high. And in this case, on Earth, with water, that's just over 30 feet. Okay, what does this have to do with anything? This is how the earliest devices for measuring pressure were built. And this is called a barometer. And so if we look at the basic function of a barometer, it's what I just built. It's an inverted tube that's closed on one end in a container, an open container of a liquid. Now, so how do we build it? Well, we cover the end, we fill it up completely. Notice there's no air in here. We cover the end and we invert it, just like I did, just like I just demonstrated. If you had a 30-foot long or 30-foot tall cup, 35-foot tall cup, then you would notice that you got a little bit of separation here. Again, it's a vacuum up here. Now, that's not very practical. To make a real water barometer, you need 30 feet plus. A more dense fluid would make that easier, though. The densest fluid around is mercury, so the original barometers were made out of mercury. Now, you need 30 feet of water. It turns out you don't need nearly as much mercury. In fact, you only need 760 millimeters of mercury. It's about 3/4 of a meter, and it's just over 2 feet. So we're looking at about like that, right? So if I had a bucket of mercury, which I don't, then I could probably demonstrate this, right? I could probably find myself a container that was 2 feet long, but I don't have that much mercury. So you'll just have to take my word for it. Again, back to this idea, right? The greater that the air pressure is, the harder it pushes down on the outside of this container here, or excuse me, on the surface of the water here. The greater air pressure is here, the harder it pushes down, the farther it can push this column up here. So on a day when air pressure is low, this column is a little bit lower, maybe down to here. And on a day when air pressure is extra high, then it might be more like up here. That's the basic functioning of a barometer. Invented by an Italian, Mr. Torricelli, in the 1600s, actually. So this is quite an old idea. Pressure units, we went over these briefly in the last chapter. You don't have to memorize this stuff, but just recognize there really are a lot of different ways that pressure is commonly measured. Pascals, that's what we use in this class. This is our standard SI unit. Atmospheres, super handy. You use them a lot in chemistry class, right? 1 atmosphere is sort of this average of pressure at sea level. But of course it varies depending on the weather, all kinds of stuff. So it is definitely just an average. We can measure it in millimeters of mercury also. And so 1 atmosphere is equal to 760 millimeters of mercury. But in real life, that would go up or down a little bit every day. Of course, you could just convert that to inches, right? So that's about 30 inches of mercury. If you listen to the weather report, they'll tell you what the barometric pressure is. The barometric pressure is 28.5 inches and falling, right? What do they mean? They mean 25.8 inches of mercury. It means that the air pressure can support a column of mercury that's 28 inches high. Pounds per square inch. This is what you would use if you were an engineer in the United States. If you're pumping up your bicycle tires, that's also probably what you use.